Welcome to Eager Space. My latest video on nuclear thermal rockets being mostly pointless generated a lot of comments, many suggesting that I chose the wrong sort of mission or spacecraft for my model, and further suggesting that I should look at interplanetary missions. I didn't do that because I wanted to provide a simple explanation, but I am nothing if not amenable to suggestion. How about a nice trip to Mars? How would nuclear thermal work in that scenario? It turns out that NASA has done most of the work for us, with a series of increasingly detailed reference architectures for missions to Mars. The most recent one is the 5.0 version. The main 100-page document was published in July of 2009, and a 406-page addendum was published at the same time. It was updated with a 598-page second addendum in March of 2014. We have plenty of detail to go on, and do not have to depend on a model that I create. Mars missions present many different options, such as departure date, as different dates require different trajectories and more or less delta V to get there. Whether the mission occurs all at once, or whether a cargo mission flies before the crewed mission. What method is used to enter Martian orbit, whether it involves aerobraking or propulsive braking. Whether solar or nuclear power is used to generate power on the surface. Whether the propellant to get off the surface is carried with the lander or is generated on the surface. And, the reason we are here, how different propulsion choices affect the mission. NASA plays with different choices in these documents, and that can make it hard to do comparisons, but there is a good baseline we can use. We're going to start with the nuclear thermal architecture, since that's why you came here. Our launch vehicle for this reference architecture is the Ares 5 that was proposed as part of the Constellation program. It is specified as being to take about 110 tons of payload into a 400-kilometer orbit. The first part of the mission is 2 cargo vehicles that will aerobrake into Mars orbit and then land on the surface. The propulsion system uses 3 nuclear thermal rocket engines that are almost assuredly the SNRE enhanced engines I talked about in the previous video. They put out 111 kilonewtons of thrust each, or pretty much exactly what an RL-10 engine puts out. The vehicle is much too heavy to be launched all at once. The first 2 launches will carry 2 propulsion modules, one for each cargo vehicle. They mass 96 tons each. The third launch carries 2 liquid hydrogen tanks, each with a mass of 47 tons, one for each cargo vehicle. The fourth and fifth launches carry the actual payloads, each clocking in at 103 tons. That's 5 launches in total, and each cargo vehicle masses 246 tons. There are no external radiation shields for the cargo vehicles. The assumption is that the payloads will not be affected by the radiation of the engine. The cargo vehicles travel to Mars. The assembly of the crew version starts. The first part of the crew version is the same propulsion module as the cargo vehicle, except this one has an 8-ton radiation shield outside the engine to protect the astronauts. It has an inline liquid hydrogen tank and a liquid hydrogen drop tank. And then finally the last truss, the transit habitat where the astronauts will live, and the docked Orion module and service module. That gives us a 356-ton crewed vehicle that can be assembled in 4 Ares 5 flights, and a total mission mass of the crew vehicle and 2 cargo vehicles of 848 tons launched on 9 flights. That's about double the mass of the International Space Station. This is a big vehicle. The assembled crew vehicle is about 80% the length of a Saturn V. Now let's look at the chemical architecture. The propulsion system is based on a self-contained TMI, Trans-Mars Injection, or Earth Departure Module. They mass at 104 tons, so you take 2 of those in line and add in the cargo module, and there's a total mass of the cargo vehicle of 310 tons. That pattern is repeated for the second cargo vehicle, which means 6 flights to assemble the 2 cargo vehicles, except that this approach requires a 7th launch of 2 reboost modules to keep the cargo vehicles in orbit while they are being assembled. More on that in a few minutes. The chemical architecture gives us a cargo vehicle that is about 25% heavier than the nuclear thermal one, and takes 40% more flights to get into orbit. For the crew vehicle, the crew module flies first with a reboost module. A second flight brings the Trans-Earth injection stage and the Mars orbit injection stage, and then 3 flights for the TMI modules that will send the crew on their way to Mars. That's a 486-ton crew vehicle assembled in 5 flights, and the total vehicle mass is 1,106 tons over 12 flights. Not surprisingly, it's a heavier option. Let's take a look at the mission costing for the 2 alternatives. I don't have a good cost for Ares 5 launches because it was never built. SLS is a smaller vehicle than Ares 5 and is estimated to be about $2.5 billion a launch. I'm going to use $2 billion per launch as an estimated cost for this model. With that, the estimated launch cost for the chemical architecture is $24 billion for 12 launches, and the nuclear architecture is $18 billion for 9 launches. That's a $6 billion difference, and that is a meaningful amount. It's the main driver of why the nuclear model is considered superior. We will need to look at development costs. In actual dollars, Nerva cost about $2 billion, and the Saturn V cost about $6 billion. Converting to 2025 dollars, it's pretty close to a factor of 10. So $20 billion for Nerva and $60 billion for the Saturn V. The SNRE enhanced engine proposed for this would obviously leverage the Nerva development work, but working with nuclear materials is vastly more expensive now than it was in the 1960s. I'm just going to put in a range of $1 to $4 billion. We'll add in that engine development cost here, and since the chemical architectures use existing engines, there's no development cost. Feel free to note that the nuclear engine development cost only applies to the first mission. You don't pay it for further missions. We do need to buy the engines for missions. By my count, we have 27 RL-10 engines, and at $10 million each, that's $270 million for engines. My guess is that you might be able to cut that in half with a big order to Aerojet Rocketdyne, or you could redesign to use Blue Origin's BE-3U upper stage engine instead. You would need a lot fewer engines as the BE-3U is a beast with much higher thrust. You need 9 nuclear engines for the mission, and I'm going to assert that you will spend at least $1 billion for that set. And I'm going to just allocate $1 billion for the stages themselves. In reality, the chemical stages are likely to be cheaper because they are standard construction, and the nuclear hydrogen tanks are higher tank and will need development money. Add all that up, and we get a little over $25 billion for the chemical architecture, and somewhere in the $21 to $25 billion for the nuclear option. The nuclear option still looks cheaper, but it has a lot of development risk because of the engine. It also carries more schedule risk. It does have the upside that some of that cost goes away if you have future missions. But I'd like to talk a little bit more about the reboost modules. The section in the module says the following. The reboost module was required due to the long on-orbit assembly time and the mass of the vehicle that is being assembled. There's a nice chart in the document that shows the timeline for the vehicle assembly. This is for the cargo part of the chemical propulsion architecture, which has the longest timeline. The 2 reboost modules are launched by themselves 270 days, 9 months before the launch window to Mars. Then a module is launched every month, and the cargo vehicles are assembled as new modules are launched. There is a 2-month open period at the end to finish assembly and to provide a bit of buffer before you head out to Mars. There's a significant problem with this architecture. And the problem is that it depends on all your modules being ready to fly on time and launching consistently every 30 days for 7 months. Maybe you can do that. SpaceX has been flying Falcon 9 with high consistency, so it's possible. But the problem is that if you are late for your TMI window, you're dead. This is a map of the available Mars transfer windows, with the color indicating how much delta V is required and the vertical showing the travel time. These are what are known as conjunction windows. You want to leave one planet when it is behind the other so that you will conveniently reach the orbital diameter of the target planet right when it gets there. That gives you the cheapest transfers in terms of delta V. Let's say that you are aiming for this block, but it turns out you couldn't launch fast enough. Some of your payloads were late, or you had problems with assembly. Typical spaceflight problems. I have some very bad news for you. Your next target isn't a month away like a lunar mission. It's 26 months from now, the next time the planets are in alignment. You have spacecraft in deteriorating low Earth orbits waiting for you to launch, and you're going to have to keep them in orbit for that 26 months until you hit the next window. I'm really surprised that this timeline ended up in any document. It's such a bad and unrealistic idea. It would make much more sense to launch a year before your departure date. The reboost modules are intended to be sufficient for a full year, and that gives you a lot more options. But you might have noticed that the nuclear thermal option does not include reboost modules. That means you get to drop your vehicles in the ocean if you get behind, which would be bad. I therefore think we should add them to the nuclear thermal option. It will take one extra flight. The crew habitat flight has enough extra payload capacity to carry a reboost module with it. That pushes the nuclear variant up to 10 flights and pushes the total cost up to $27 to $27 billion. Just one additional flight makes the two architectures a lot closer in cost. Let's look at some other options. Ares 5 is 110 tons for about $2 billion. Falcon Heavy has a published payload to low Earth orbit of 63 tons, though the rocket isn't actually strong enough to launch that much mass, and you would need some big fairing improvements to fit the Mars modules. My guess is that that's a $200 million rocket for this mission. The newly announced New Glenn 9x4 is projected to do 70 tons to low Earth orbit. We have no published prices, but my guess is that it's roughly a $300 million rocket for NASA missions. We'll need to redesign our architecture into smaller blocks, and that does complicate things, which will drive up the cost of that part of the program. We double the number of flights, but at these low prices, there's only a small difference in launch costs between the two options. Our transportation costs go way down, and that reduces the cost of the extra mass of the chemical option, and that means that the nuclear development costs and the engine costs are much more impactful. The result is that the chemical architecture is at least competitive with the nuclear one, and might end up being cheaper. It's almost certainly faster. This is the reason that DARPA decided to cancel Draco. It's only worth putting the money into nuclear thermal engine development if your launch costs are high enough that the mass of your vehicles matters a lot. And this is based on the costs of partially reusable rockets that are flying. If Starship ends up being reusable and cheaper than these options, then there is even less reason to go nuclear. I do want to talk about two other architectures. The 5.0 architecture second addendum explores two additional options, nuclear electric and a hybrid option combining solar electric and chemical propulsion. Both of those end up being lighter than the nuclear thermal option and can therefore be done with fewer flights. Unfortunately, these are both lower thrust versions and they take a long time to get there. The chemical and nuclear thermal versions take about 380 days in travel to Mars and back to Earth, and spend about 500 days on the surface. Nuclear electric takes 533 days for travel to spend 400 days on the surface, and the solar chemical hybrid spends 765 days traveling and only 300 days on the surface. None of these make me excited about missions to Mars. Even with the fast versions, you're spending roughly 6 months in space each direction, and the total mission time is more than 2.5 years. That is a long time to be away from home, and I think you're going to get seriously bored spending 300 to 500 days on the surface of Mars. So where does that leave us? Well, I reassert that in the current launch world, nuclear thermal engines are still mostly pointless. In the last video, I neglected to mention Winchell Chung's incredible Atomic Rockets website. If you want to know what sort of specific impulse you will get with a nuclear thermal rocket using ammonia, it's there. If you need help designing nuclear propulsion devices for your Orion rockets, it's there. I cannot recommend this site enough. That's all for this video. Today's song is You Can't Always Get What You Want, from the Rolling Stones' 1969 album, Let It Bleed.